Well, welcome back to our course on system engineering. In this lecture, we're going to be talking about systems security engineering. And just to give some context, this is the second of 3 lectures that we'll be talking about systems domains. And so we're getting close to the end of the chapters, the end of the lectures for this course. So let's go ahead and get into it. So first, let's talk about systems security engineering. Systems security engineering is a domain of system engineering and may be considered complementary to systems engineering development. Also called SSE, the SSE engineer must be able to coordinate security-related efforts and designs and also seamlessly integrate with the rest of the system engineering team. So for this first section, it starts with common definitions of SSE. It discusses the roles of the SSE engineer and explores the motivations of why SSE would be needed in system development. SSE originates from the Department of Defense, Homeland Security, and law enforcement efforts, with many of these systems they develop involving a great deal of security as they require security operations, access to sensitive data, and deal with national and personal security implications. Some of the initial SSE definitions originated from the DoD sources, and there's a reference that's given in the textbook MIL HDBK 1785. And so it's cited as a definition, an element of systems engineering that applies scientific and engineering principles to identify security vulnerabilities and minimize or contain risk associated with these vulnerabilities. It uses mathematical, physical, and related scientific disciplines and the principles and methods of engineering design and analysis to specify, predict, and evaluate the vulnerabilities of the system to security threats. Other sources expand on the definition to include the prevention of misuse and malicious behavior on the system, protection of sensitive data, processes, technology, and intellectual property. Regardless of the source, the SSE approach is to enhance security on the development concept that is under development. The SSE engineer must possess the ability to look at the system from a holistic perspective and view the system security practices, vulnerabilities, risk, and opportunities from a variety of perspectives in order to develop an encompassing and adequate security protection capability. The SSE engineer must also be able to generate much of the initial systems engineering artifacts in the initial phase of development as the rest of the system engineering team and be able to integrate the SSE capabilities within the given development schedule. The SSE engineer may also need to conduct trade-off analyses in order to present the overall system leadership, the implications of incorporating particular security capabilities within the system. Sometimes this may be at odds with other designer objectives, which may de-optimize efficiency for security. Other conflicts may include access constraints, lack of design flexibility, and additional testing and operational constraints against the original design. The motivation for SSE comes from a variety of sources. From the defense domain, numerous threats are motivated to defeat the system under development, either directly through causing disruption or degradation of the original system's capabilities through direct interaction with the system and the interfaces. Other efforts may be more indirect, such as containing the supply chain processes, where inserting malicious processes during the system development could provide the adversary with an opportunity to degrade the system at their convenience, typically during critical operations. The DoD has identified 3 motivations for improving SSE: their system's reliance on commercial technology, the susceptibility of supply chain contamination, and the increasing system complexity and interconnectedness. Non-defense domains also have similar security concerns with the increasing complexity of systems. For example, modern Automobiles have over 150 million lines of code in their microprocessors. Other automotive systems may also increase the connectivity to other systems, such as maintenance, marketing, or organizations that may increase the risk of malicious activity through increased attacks. Automated systems that interact with external networks without human intervention are especially vulnerable. Voice and mind activation, seeking information, and manipulating technologies are excellent targets for abuse. Healthcare and financial organizations may also have increased concerns for SSE efforts to ensure that data integrity and privacy are not violated. Security concerns go beyond computers, networks, and software, as vulnerabilities can rapidly develop and do serious damage to the infrastructure, privacy, and viability of current and proposed systems. Security systems must be able to continuously and rapidly respond to new and evolving threats for lifecycle protection and awareness of emerging technologies. System security strategies recognize the adversaries are highly competent, often applying multiple technical agents that can identify seeming small weaknesses that can easily take the system down. High system complexity in itself may increase vulnerabilities if system security is not fully addressed. Ideal protection may include system thinking for self-system preservation. This often asymmetric threat advantage implies that cycle defenses that can be quickly be evaluated with defensive elements integrated into the operational system. Cybersecurity systems and devices need reliable privacy and resilience, hence security elements must be integrated into the system design. Okay, well, let's talk about the types of security. So the SSE engineer should evaluate the system concept under development from a critical eye and identify the mission critical areas that could significantly affect the system's operation, either through its internal function or external interfaces with other systems, people, or organizations. An integrated security and systems engineering process will benefit from a careful review of prior vulnerabilities and threats, engaging security experts and risk mitigation practices. So let's go through these one at a time. First, critical function analysis. The SSE engineer can evaluate the system operation through analysis of the functions and interfaces that the system performs. The SSE engineer may rely on their own security knowledge or need additional consultation on how the system may work to properly assess the criticality of these functions. Often a functional decomposition will assist the SSE engineer to identify the critical functions that may have significant impacts on the entire system operations. Other views may require some analysis to determine if functions at critical phases in the system operation may adversely affect the overall performance. Operational analysis using degraded functions may also identify selected functions that would need to be protected or hardened. Then we have critical interface analysis. As today's systems are increasingly interconnected and require external interactions to successfully complete their objectives, the SSE engineer may also evaluate these critical interfaces that inadvertently cause a system to fail or produce a less than desirable result. A sequence diagram to analyze the interfaces and sequences of interactions may identify critical junctures where dependencies on external systems may affect the system overall performance. SysML models can be queried. These queries may be displayed in tabular or matrix form. Alternative interfaces or sources may be recommended based on the criticality of interface or knowledge of trust in the dependencies. Knowledge of how the system will react based on correct or incorrect data coming through the interfaces may provide insight into the level of importance to the system. Next, we have access to the system. Many security professionals look at malicious outsiders attempting to enter the system, although the SSE also needs to consider the insider threat that is already inside and operating the system. Unrestricted access from any user may be perilous to system operation. If it was intentional or unintentional, the SSE engineer should consider all the different roles and users that will access a system, in what capacity and what level of access is possible from their role. Implementing protections such as role-based access may help limit unnecessary access by other users that interact with the system. Moving laterally through the system may cause harm to the system. Evaluating how much access that the user should be evaluated to determine how vulnerable the system is to the inside threat. Red teams are well versed in exploring the available access that is not visible to the decision makers. Next, we have system physical security. As much of the attention is paid to the cyber and data information security, the SSE engineer should also consider the physical security status of the system and its supporting infrastructure. This may also provide additional access points for malicious threats and unwitting users to access the system and cause irreparable damage to the operations. Areas of importance to the system, such as data centers, user terminals, or maintenance access ports, are just a few areas that should have some physical security measures. Typically, the areas inside of a security perimeter are left unlocked or open, presumably based on the assumption that the external protective behavior is sufficient and are ripe for exploitation. The SSE should collaborate with the physical security officer to identify easily accessible areas within the system's boundaries in an effort to strengthen the areas that may be more susceptible to exploitation. Next, we have data security. Data security is important to the system operations, both at rest, in transit, and in use. Data at rest is typically stored in the system or in an external data storage system in the form of databases, data warehouses, archives, tapes, backups, etc. If the data is not being used, it is considered at rest and should be protected from unauthorized handling, evaluation, or use. Data in transit is data that is being retrieved and transferred from one site to another. The SSE should reduce the possibility that this data could be intercepted or corrupted. Using network security solutions, data protection solutions, and encryption protocols may assist with the protection of this data. Finally, when the data is at the endpoint, users are able to interact with the data, preventing unauthorized copying, manipulation, detection, or other malicious activities should be the goal for the SSE. Use of strong user authentication, identity management, and profile permissions are examples of how security may be maintained. With any organization, a robust training program and continuous monitoring of the security can aid in the successful security program. Next, we have operational security. The system may have the best security practices, but letting someone discuss critical information to the outside world may nullify all the security available. Ensuring that only authorized users have access to need to know will have access to the system's critical functions and operations. Sometimes knowing about seemingly unrelated operations that are connected to the system operation can alert adversaries to find alternative paths to exploit the system, such as upcoming tests or an increased dependency on services from other organizations. Evaluating the external footprint of the system during development and operations may also lend insight into the security of the program. Again, red teams can conduct open source intelligence by trawling the internet or chat boards to determine if there are any critical programs under development. Finally, for security framework, having a proper framework to evaluate the program security may also provide a guidance and proper application of resources to the program. The NIST Cybersecurity Framework, CSF, offers a basic framework that can be applied to any program to implement security. The first step is to identify phase, to determine what the critical nodes are in the system that require some protection. The second step is to protect these critical nodes with the available protective technologies and methods. The third step is to detect and monitor for malicious activities against the system with the defenses that were just installed. The fourth step is, if the system is attacked, is to defend against the malicious efforts against the system and to repel any damage or activity. The fifth step is, if the system has been damaged, is to recover to an acceptable state of operation and restore critical capability for users to continue system operation. So in this figure, we provide a context diagram view of the system security, and which helps to identify areas to look holistically at the entire system concept and ask several questions. One, what are the most critical functions of the system? If they were corrupted or degraded, would the system be able to complete its mission? Two, what are the most critical interfaces of the system? If these interfaces could not be connected or successfully transfer the desired elements of information or have the intended effects, would the system be able to operate successfully? What would be the impact on other dependent systems or organizations? Three, is the access to the system. What is the access to the system? Is it wide open or controlled? Are there ways to circumvent the process? And are there ways from authorized users in one part of the system to access the remainder of the system? What types of commands and actions could they conduct? If this was possible, what would be the impact on the users? What if there were unintentional but still incorrect commands that users could execute? How would the system respond? Four, what is the physical protection of the system? Are there specific areas for the direct system control, maintenance access, or data repositories that may be available to anyone without proper authorization and access? Five, what is the state of the data that the system operates with? Are there proper safeguards for data that reside at rest within the system? What about data security when it is in transit from one system to another? And six, is the data on critical functions of the system readily available with open source or public areas of access? Are critical operational details available to anyone without proper access and need to know? And then finally, number seven, are critical components of the system identified to employ additional protection capabilities? Are these components given adequate protection? Are there capabilities to detect malicious activities? And if detected, are there adequate response features to be implemented? Are these sufficient recovery plans in the case of malicious action? Okay, well, let's talk about security applications to system engineering. SSE may be applied to different aspects of the systems engineering lifecycle as the system concept is under development. The SSE engineer must interface with the rest of the system engineering team to develop the security requirements, identify security functions and designs, develop the architecture that the system must implement, integrate the security capabilities during the development and integration cycle, and finally execute the security testing, the installation and test phases. So in this figure, we're seeing it's used to assist in identifying where SSE could be applied with the SE lifecycle process. So on the last slide, we were showing these things that the SSE can perform. And so I'll go through these one at a time, but we'll use this figure as a backdrop for capturing that. So for security requirements, the SSE engineer may need to elicit requirements from different actors of the system concept that is under development. Some of these requirements may emerge from understanding and documenting normal operation of the system, while other requirements may be created on what could go wrong with the system. This may be from red team members that intentionally seek out flaws and errors in systems in order to identify areas for improvement, while other inputs may be from making errors while operating the system. Requirements may also come from evaluating and studying of other similar systems that may have been previously attacked and or failed, so as to inspire additional security requirements. Study of the threat and how it evolves can also provide additional requirements. Next, for security design and integration, as the SSE engineer understands the security requirements that the system concept must perform, there will be options on how to execute these requirements with appliances, applications, training, or skills that can help address these requirements. As the solution space is considered, equal consideration must be given to how these design solutions would integrate within the rest of the existing system or the future system components. Going through use cases and scenarios to understand how the security appliances must work with the different parts of the software, hardware, or users can provide additional insight on what information and interfaces are needed to succeed in the use case. SSE integration may also need to consider other trade space within the system concept and may need to adjust the design performance based on other decisions made for the final system design. Then for security testing, during the testing phase, SSE engineers will also need to ensure the system concept has the proper testing of the security capabilities, in addition to the conventional system performance testing. Coordination between the security and non-security testing will need to occur in order to minimize duplication of testing resources and maximize coverage of testing objectives. As mentioned in the requirements phase, there may need the use of the red team that understands the threat concept and tactics in order to test the system under realistic conditions and adversary capabilities. Equally important to the system testing is the understanding of the system condition when under security testing, and to evaluate whether the system can comprehend the system status and maintain situational awareness while the system may be compromised. This may be challenging to adequately test this comprehension if the system status is not readily apparent or provides a visible status change. Then there's security in the supply chain. Not only will the system be evaluated during the operation, but also during the sustainment phase through the supply chain, as faulty spare parts and updates may cause a system performance to degrade. Other issues with a corrupted supply chain could have the fault remain dormant until critical operations or command is needed. Sufficient measures should be evaluated while the system is undergoing periodic maintenance as well as long-term upgrades and improvements. And for security in the operations and maintenance phase, while the system is in operation, the SSE engineer would be interested in ensuring the proper security is maintained during these phases. This may include operational security regarding the deployment plans or operational techniques that the system will employ. This may include physical security on the actual system, support components, facilities, and personnel that work to service the system, which may include third-party vendors and foreign country support organizations. Public release of information that could provide valuable insight into the system capabilities and limitations should also be checked to make sure that inadvertent disclosure of the information is not provided. And we have security in the disposal phase. Once the system is ready for disposal, the SSE engineer must ensure the residual information, data, or technology does not exist that any scavengers can extract from the system once disposed. This may mean that the use of clearing and destroying the memory from information systems, physical components that can provide valuable intelligence or corporate/manufacturing secrets that could be replicated, documented regarding or operations and maintenance procedures, or personnel that need to be debriefed, and encouraged not to divulge proprietary or classified information. Okay, there's also security applications to domains. There are numerous applications of SSE that can be applied to different domains. This includes our several representative examples of different domains and how SSE could be influence the system engineering lifecycle. And so we're just listing a handful of those different types of domains that you can see here on this chart. We'll talk to those here while we're showing this figure, where this figure provides some areas for which SSE could be overlaid into the domain requiring system engineering. First, defense and homeland security. Defense systems rely on security measures in order to protect critical and proprietary manufacturing formulas, unique operating capabilities, and maintaining their capabilities during the operational period. SSE engineers are keen to ensure that intruders are kept out of the system, as well as ensuring that the insider threat does not leak information out early either. Security issues may also be a concern when operating with partnering organizations and or countries that may knowingly or inadvertently release sensitive information regarding the system. In terms of transportation, the SSE engineer looks to ensure that transportation systems are safe as well as efficient to serve their intended population, ensuring that the systems work properly in light of operation, and passenger attempts to cause the system to fail would also fall into the SSE engineer's concerns. Complying with social as well as technical guidelines to ensure safe operations of the system is also key for a successful transportation system. In terms of agriculture, the SSE engineer may also be concerned with the agricultural system safety to ensure that the system will perform as needed in a safe manner, both for the operator safety and for the products that are handled and produced in the agricultural domain. There may be concerns with the amount of fertilizer or other chemicals that may come into contact with the food products that are being developed, and may be concerned with their system following technical and agricultural regulations. And finally, we have critical infrastructure. Similar to the transportation sector, there are other critical infrastructure sectors that the SSE engineer may be involved in to develop security requirements, integration, and testing of systems. Work with the appropriate government officials, users, regulatory bodies, and understanding of the environment that the system will work is a key to the applying the relevant security capabilities within the system. We also have security validation and analysis. The SSE engineer must be versatile to acquire and develop complementary skills and the rest of the system engineering team in order to ensure that the system concept has sufficient security capabilities during the development phase. So in this section, in this part of the lecture, it identifies different skills that the SSE engineer may acquire to meaningfully contribute to the SSE project, to the system engineering project. The SSE engineer would serve as a similar capacity as other members on the SSE, on the system engineering team, and they will focus on the security aspects of the system's interfaces with external entities and organizations, as well as focusing on the internal security processing of the system itself. This may require additional understanding of the external connections that the system has, to include permissions, access control, rule set for allowing or denying connections, as malicious processes may originate from outside the system and be transmitted for infection. The SSE engineer will also need to understand the internal system and software processes that operate the system to ensure that malicious processes are not inadvertently activated based on the logic and security settings. Understanding how certain systems processes may be affected by security measures is also a key. An example being time-sensitive calculations or processing that may be slowed by security checking. The SSE should be judicious in their allocation of security measures so as to not adversely affect the system's operation. The security testing analysis performed by the SSE will also be key to ensuring that security controls and measures will not interfere or degrade the system operation. Refer to the system approaches described in a previous lecture and chapter to integrate with the SSE testing efforts. SSE will also need to consider security updates to implement during system life cycles, as security patches are regularly deployed based on security research, as well as ad hoc deployments based on outbreaks of malicious code that may infect a large amount of systems. As many of the deployed systems are operating continuously, they may be little time or opportunity to take these systems offline and update their security features. So a means of identifying and updating the entire portfolio of a system on a regular basis should be developed. So in this table, it provides a listing of the interfaces that an SSE engineer would interact with other system engineering team members. So you may want to pause the video and just review that. Okay, well, let's just finish up with a summary review, and we'll just go over the key concepts that we talked about. First of all, system security engineering. SSE needs to be part of a system engineering process in order to provide sufficient security to enable the system to successfully execute its mission. The SSE engineer should take a holistic view of the system in order to identify what types of security may be needed to protect against threats. We also talked about types of security. The SSE engineer can examine the system in order to determine what types of security is needed. Selected areas and questions may be posed to evaluate the system security include critical functional analysis, critical interface analysis, access to the system, system physical security, data security, operational security, and security framework. We also discussed the security applications for system engineering. SSE may be applied to different aspects of the system engineering lifecycle as the system concept is under development. Selected areas that the SSE engineer can perform include security requirements, security design and integration, security testing, security in the supply chain, security during operations and maintenance, and security during disposal. We discussed security applications to domains. SSE engineers can apply their security approach to different domains. Some of these may have common artifacts and needs for security, and some may have unique security requirements. Some types of domains that could be applicable are defense and security, transportation, agricultural, critical infrastructure, and other domains that rely on secure means of communication and interactions to succeed. And finally, we talked about security validation and analysis. SSE engineers may need to interface with multiple parts of the system engineering team and will require some coordination to successfully insert and integrate security details within the system concept, requirements, design, and testing. Okay, well, thank you very much. That'll end this lecture.